Hi, welcome to Why News Reports of Scientific Results Need to Include the Error Bars. The current best understanding that we have of particles and their interactions is the standard model of particle physics. It predicts the values of many quantities to remarkable precision. A particularly impressive example is a quantity called mu on g-2. It is currently of great interest because the standard model prediction and the measured result from the mu on g-2 experiment at Fermilab show a statistically significant deviation. But even that unexpected deviation is at the level of 2 parts per million. For more information, you can check out the playlist mini-series on g-2 of the muon on this channel. As successful as the standard model is, it also leaves a lot of questions unanswered, like the nature of dark matter and why there are 3 fermion families. So despite its success, it's not a complete theory of nature. Because of this, we hypothesize about new models of particles and their interactions that might answer these questions. So we do experiments to test 1, the predictions of the standard model, to see if it continues to agree with observation or shows signs of failure, and 2, the predictions of these other models to see if there's evidence for them or if we can rule them out. These experimental tests tend to get more precise as time goes on. These experimental tests take the form of measurements. We measure things like particle masses, particle lifetimes, the probability for a particle to decay to a certain set of particles, and the rates of processes in collider experiments. We see if the results of these measurements agree with the predictions of the SM and other models. Okay, so let's imagine a scenario. Let's say that a news story reports a recent result from a particle physics experiment. To be concrete, let's say the experiment measured the lifetime of a certain particle. Now, let's say the news story reports that this new result disagrees with the prediction of the standard model. But let's also say that this experiment was not the first to measure the lifetime of this particular particle. A few years ago, another experiment measured the particle's lifetime, and they got a result that agreed with the SM prediction. Does this mean the 2 experiments disagree with each other? Is this an inconsistency? And the answer is not necessarily. Let's see how that can happen. In order to answer this question, let's briefly take a look at a few important points about error bars. Okay, so we want to measure the lifetime of this particle. Let's call that lifetime tau. Now, no experiment is perfect, so that means that the value that we get when we do the experiment is not going to be exactly equal to the true value. So tau measured will not equal tau true. The difference between the measured and true values is called the error. So here the error would be tau measured minus tau true. The term error does not indicate that a mistake has been made. It is only a reflection of the fact that measurements are not infinitely precise. When we do a measurement, we'll get a value for tau measured. But we don't know the true value of the lifetime, tau true, so we cannot know the error for a specific measurement. But through careful studies of our measurement apparatus and techniques, we can estimate how large the error will typically be. To express this estimate, we quote an uncertainty on the measured result. In particle physics, we typically express uncertainty in terms of a quantity called sigma. This terminology comes from the case of Gaussian errors, which we will assume here. For lots more information on what Gaussian errors are and when they arise, you can check out the playlist Brief Introduction to Gaussian Errors, available on this channel. All error bars in this video will be in the form of plus or minus 1 sigma error bars. So for example, let's say a new particle was discovered and its mass was measured to be 937 plus or minus 42 GeV over c squared. Here, 937 GeV over c squared is the measurement's central value, and 42 GeV over c squared is the uncertainty sigma. Let's plot this measured result for the particle mass. It covers a range. The central value is in the middle of the range, and the error bar extends by 1 sigma to either side of the central value. Now, sigma can be viewed as a typical size of the error. It's not the case that the true value of the measured quantity has to be within the plus or minus 1 sigma error bar. Let's go back to our particle lifetime measurement and see how the measured result, tau measured, relates to the true value, tau true. This is a plot of the probability density for tau measured, assuming Gaussian errors. Let's say that the experiment to measure the lifetime were repeated independently many times. This plot tells us how the measured results would fall around the true value. In approximately 68% of measurements, the measured value tau measured will fall within 1 sigma of the true value tau true. Approximately 95% of the time, tau measured will fall within 2 sigma of the true value tau true. And approximately 99.7% of the time, the measured value will fall within 3 sigma of the true value. The measured value tau measured will sometimes fall much more than 1 sigma away from the true value tau true, but it will happen only rarely. So you might sometimes hear something like that a measured result fell 3.2 sigma away from the standard model prediction. Under the hypothesis that the SM is correct, this is a somewhat unusual result. It's enough to get physicists interested, but it's not enough to convince them that something new is going on. In particle physics, it's customary to not consider an experimental result a potential discovery unless it disagrees with the standard model prediction by at least 5 sigma. If a measurement disagrees with the SM prediction by at least 3 sigma, sometimes physicists will start saying that there is evidence for new physics. If you'd like to get an idea of how strange an observation like this is, you can check out the video Getting a Feel for the Meaning of 1 sigma, 2 sigma, 5 sigma, available on this channel. So if a news report says that an experimental result disagrees with the standard model prediction, this is quite vague. How much does it disagree? 2 sigma, 3 sigma, 5 sigma? These are very different levels of disagreement. And if a measurement agrees with the SM prediction, that doesn't mean the experiment got the same answer as predicted by the SM. Typically, it means the measurement and prediction agreed within 2 sigma. But here's an important point. How much 2 results, or a result and a prediction, disagree with each other depends on their error bars, not just the difference in their central values. For example, let's look at these 2 hypothetical measurements. They are in fairly good agreement. Their error bars don't overlap, but they are easily within 2 sigma of each other. On the other hand, we can look at these 2 measurements. Their central values are closer to each other than those of the pair we just looked at, but their error bars are much smaller. They disagree strongly by several sigma. Okay, So now let's look back at our original question. A news report says that a new measurement of a certain particle's lifetime disagrees with the prediction of the SM, but a previous experiment measured the same thing and got a result that agreed with the SM. Can these two experiments be in agreement with each other? From what we've said up until this point, we can probably guess that we'll see that without knowing about the error bars, we can't know if two experimental results are in good agreement with each other or not. Let's see a couple of ways that this situation can arise. Okay, so we're going to plot the SM prediction and the results of the two experiments. Here is the standard model prediction. Note that the standard model prediction will itself have an error bar. If you'd like more information on why that is, you can check out the video, Why Do Scientific Predictions Have Error Bars? Available on this channel. Again, this error bar represents the central value of the standard model prediction, plus or minus 1 sigma, where sigma is the uncertainty on the prediction. Okay, first let's look at one way that this can happen that is not so interesting. It could be that the new measurement, shown here at the top, falls fairly far away from the SM prediction, such that we would say it disagrees. While the old measurement fell in between the standard model prediction and the new measurement, we might consider the old measurement to be in agreement with both. Okay, that's not very interesting. Now let's look at a second way. This is more interesting because it shows the role of error bars in determining whether results agree or disagree, and because it reflects reality. Usually error bars shrink with time as experiments improve. So again, we have the standard model prediction. It could be that the old measurement had quite a large error bar. Because it had a large error bar, it was easily in agreement with the standard model prediction. And now a new and improved experiment makes a measurement with a much smaller error bar. As shown here, it's just outside the error bar of the old measurement. The new measurement is in good agreement with the old measurement, just much more precise. And because it is much more precise than the old measurement, it is able to disagree sharply with the standard model prediction. Its central value has moved over to the right, but its error bar is much smaller. Because the old measurement had such a large error bar, it could be in agreement with both the prediction and the new measurement, even though the new measurement and the prediction don't agree with each other. Just saying that the old measurement agreed with the standard model prediction doesn't say much. The old measurement had such a large error bar that it would agree with a large range of predictions or other measurements. Or, more generally, a measurement with a huge error bar will agree with lots of hypotheses. It doesn't confirm any of those hypotheses. It just doesn't have the precision to rule them out. If a report only says that a measurement agrees with a prediction, that doesn't give us as much information as one might think. We need to ask ourselves, okay, the measurement agreed, but how precise was it? And how precise was the prediction? If we have measurements that agree with the standard model prediction, and then a future experiment disagrees with the standard model prediction, that doesn't necessarily mean that the future experiment disagrees with the experiments that came before it. It might disagree with the standard model prediction because it's a better measurement. The standard model might not describe nature, and this might be the first experiment precise enough to determine that.